It begins with a simple idea: time. Something you feel but never see. Something that moves but never stops. Look at a clock. The seconds pass, one by one, forward, always forward. But physics tells a different story. In 1905, a young physicist named Albert Einstein proposed something radical. Time is not absolute. It doesn't tick the same for everyone. Instead, time depends on how you move and where you are. This idea became known as special relativity, and it changed everything. Imagine two observers, one standing still, the other traveling close to the speed of light. To the person standing still, time flows normally. But for the traveler, time slows down. This isn't theory anymore. It's been measured. High-energy particles created in Earth's atmosphere, called muons, should decay in microseconds. They shouldn't even reach the ground, and yet they do. Why? Because they're moving so fast. That time slows down for them. This effect has a name: time dilation. The faster you move through space, the slower you move through time, which means if you could travel fast enough, you could go into the future. Not metaphorically, literally. Imagine a journey. You leave Earth in a spacecraft, accelerating to near light speed. You travel for 5 years. When you return, Earth hasn't experienced 5 years. It may have experienced 50 or 100. You haven't just traveled. You've skipped forward in time. Time travel to the future is real. And speed isn't the only way. In 1915, Einstein went further. He introduced general relativity. This time, gravity enters the story, but not as a force, not like a pull. Instead, gravity is the bending of space-time. Imagine a stretched fabric. Place something heavy in the center, like a star. The fabric curves. That curve is what we feel as gravity. And here's the key: when space-time curves, time itself changes. The stronger the gravity, the slower time flows. This is called gravitational time dilation. Clocks near massive objects tick slower. This has been tested with extreme precision. Even tiny differences in height on Earth change how fast time passes. And in space, the effect becomes dramatic. Near a black hole, time nearly stops. Spend a few hours there, and years could pass far away. This idea was famously explored in Interstellar, based on real physics. Again, time travel to the future is not just possible, it's unavoidable. But then, we ask the harder question: can we go back? Can we return to yesterday? Physics becomes uncertain, because going backward in time means breaking something fundamental: cause and effect. If you change the past, what happens to the future that came from it? This leads to paradoxes. One of the most famous, the grandfather paradox. Go back in time and prevent your grandfather from ever meeting your grandmother. Then you are never born. But if you were never born, who went back? Physics struggles with this. And yet, Einstein's equations don't completely forbid it. In fact, they allow strange solutions, paths through space-time that loop back on themselves. These are called closed timelike curves, a path where your future connects to your past. In theory, You could follow such a path and arrive before you left. But creating one? That's the problem. Physicists have imagined extreme objects, like rotating cylinders or cosmic strings, that could twist space-time enough. Others propose shortcuts through space-time, wormholes, tunnels, connecting distant points, not just in space, but in time. The idea was explored by Kip Thorne, one of the world's leading physicists. A wormhole could, in theory, connect two different moments, step in, and emerge in the past. But there's a catch. To keep a wormhole open, you would need something exotic, negative energy, a substance that, as far as we know, barely exists. And even if it did, we have no way to control it. Then there's another idea. What if the universe prevents paradoxes entirely? Physicist Stephen Hawking proposed something called the chronology protection conjecture. The universe may simply forbid backward time travel. Every attempt fails. Reality protects itself, but not everyone agrees. Some physicists turn to quantum theory. At the smallest scales, reality behaves differently. Particles can exist in multiple states at once. This leads to a bold idea. The universe may split into many versions. Every possible outcome happens. In that case, going back in time doesn't change your past. It creates a new one, a different branch, a different timeline. In one, you succeed. In another, you don't. An infinite web of realities. So, is time travel possible? The answer is complicated. Forward? Yes. Proven, measured, real. Backward? Possible, in theory, but trapped behind extreme physics and deep uncertainty. And maybe that's the truth of it. Time isn't just something we measure. It's something we're still trying to understand. Because the deeper we look, the less it behaves like a simple line, and more like something vast, structured, and strange. A universe where every moment, past, present, and future, may already exist, and we are simply moving through it. Not as fast as we could, but fast enough to never notice, until we start asking questions.